morning, everyone. It's great to be here. My name is Stephanie Hurder, and today I'm going to be presenting a paper that's joint work with Cathy Barrera, who's also of Prysm Group. This paper is a study of using the tools of economics to think about blockchain governance in the presence of hard forks. So before I begin, just a little bit about myself. As I said, I'm a founding economist of Prysm Group. We're a group of PhD economists who work with blockchain organizations to design their economics and governance. I have a PhD in economics from Harvard, and prior to co-founding Prysm Group, worked at the Boston Consulting Group, at MIT Sloan, and at Merrill Lynch. So because this is a mixed audience, I just want to start with a bit about why economics is an excellent tool and an excellent complement to computer science when thinking about blockchain projects. So machines are programmable, but people are not, right? You know, when we think about writing a computer program, we have to think about stochastic variation. We have to make sure that we've taken into account, all of the different things that can happen. People are not programmable. People individually optimize given the choices that they face. And so when we're thinking about designing blockchain systems, it's not enough to simply assume that the users of the platform are going to do what we need them to do. People must be incentivized to make decisions that are in line with the goals of the platform. And so the way we really view economics is that it's a great complement to computer science when thinking about designing successful blockchain projects. And of course, there are other pieces too. There's regulation, there's legal, there's marketing, there's business strategy, which I'm not going to talk about today. So as I mentioned, today I'm going to be applying the tools of economics to talk about blockchain governance. For those of you who attended the crypto economics panel yesterday, Vitalik mentioned that governance is an area that could really use more crypto economic rigor, and we completely agree. And as many of you know, governance, and especially decentralized governance, has been a persistent challenge for the industry. And we think this is a particularly promising area to apply economic insight. Economists have been studying what's called social choice for over half a century. For those of you familiar with Kenneth Arrow, he won the Nobel Prize in 1972 for his impossibility theorem, which he devised in the late 40s and early 50s. So this is an area that economists have thought a lot about. And what makes blockchain governance interesting also from an economic point of view is that blockchains can have hard forks. So if you think about the areas in which we traditionally look at governance, typically secession is very, very expensive. So for example, I live in California, and 2 years ago, after the last presidential election, there were a lot of people who were saying that they were going to pack up and move to Canada. As far as I know, nobody did, right? Secession is expensive. Whereas in a blockchain setting, secession becomes much, much cheaper. And the question then becomes not, do I leave, but do I have enough other people leaving with me to make my alternative project a viable one? And so when I think about hard forks, as an economist, one of the things that's confused me is that there's a great deal of enthusiasm for hard forks in the blockchain community. And we see things like you saw on the previous slide that say forking is freedom, all hard forks are great. And to me that's a difficult statement to wrap my head around. First, what do we mean by good? Second, good for whom, right? There are very few things in the world where they're always good. Nothing is good all of the time. And just to add to this is not a comprehensive list, but I put together a quick list of blockchain forks. And on the left-hand side, you have the ones I'm calling sustained forks. So between the time that we wrote this paper and now, I believe one of them is also on its way out. And on the right-hand side, you have dead Bitcoin forks. And this is just a partial list. But you can see that the vast majority of forks are not sustained. So it's very difficult without doing some additional analysis to say, well, forks are always good. And I think another way to think about it is that if forks were always good, the eventual outcome is that we'd all have our own personal blockchain, right? We'd all keep forking and forking and forking until everyone was alone. Obviously, that's not what we want to happen. So there needs to be a balance between cooperation and coordination and forking, and that's what we're trying to explore here. Right, so when we think about the design of blockchain governance, we want to come to the governance process to help the community coordinate on an outcome that is optimal in some way. And I'm going to be talking about the different definitions of optimality that economists use when thinking about these types of problems. But the governance process must also be incentive compatible. Your users need to choose of their own free will to do what you need them to do. And I just want to pause here and say that we meet a lot of teams who think that they can just ignore economic design, right? So they focus on the technology, and then they say, okay, I'm just not going to think about this at all. This is a design choice too, right? Just because you've chosen not to design your environment doesn't mean people aren't independently making choices anymore. They are. And the reason this is troubling is that, as we found and as I'm going to talk about right now, there are a lot of examples of economic design helping users to achieve better outcomes than they could if they were acting of their own volition and there were no design, right? So by not thinking about the design, you may in fact be not giving your users the tools that they need in order to achieve the outcomes that they want and that are good for your platform. So before digging into our paper, I just want to give you a little bit of background on a project that I think is really incredible and illustrates the potential of economic design to improve outcomes on a platform over what could be achieved without thinking about those design parameters. So for any of you who are familiar or know any doctors, in the US, when someone finishes medical school, in order to get their first job, they have to go through a centralized matching mechanism. So they interview, the residency programs and the doctors interview, and then everyone submits a rank order list that says, these are the programs I like, and then there's a central algorithm that goes and puts people with jobs and tells everyone where they're going to be working the following year. So this system has been in existence since 1900, and has gone through phases of success and failure. So in 1998, or sort of the mid to late 90s, the system was falling apart again. And what was going on were two things. So first of all, the medical students were choosing not to use the match. So rather than entering the match, they would try to find a job on their own. And then the residency programs were responding to this by also not using the match and by going out and trying to recruit people. And this had a really negative effect on the quality of jobs that people were able to get. So what you saw is that residency programs, there was something called unraveling, which is that residency programs started hiring earlier and earlier and earlier to get the candidates, which meant that they had less information about who they were hiring, so they were making suboptimal hires. And for the doctors, you could actually see that there was less geographic flexibility in where they were going. They were constrained by their own networks, and so they weren't able to get that great job across the country because there was no central facilitation. So the administrators of the Residency Match called up Stanford professor Al Roth, who was a 2012 Nobel laureate in economics, and he said, you study the theory of matching, come help us. So Al and his collaborator Elliot Perrinson went to fix the residency match. And they wanted, their goals here, they wanted to design an algorithm that people wanted to use and resulted in good outcomes. So Al Roth is an expert in an area called matching theory. Again, going back to the panel yesterday, there was a comment that all of economics is auctions. These are not auctions. This is an area of economics that's part of a field called market design. And it's matching, it's a two-sided market, it's two-sided matching when money is not necessarily used, or it's not used for its standard purpose of setting prices. And so Professor Roth had done a lot of theoretical research on matching markets. And he knew that there was this critical property called stability. And so he hypothesized, a matching is stable. So if you have doctors match two jobs, a matching is stable if there isn't a doctor and a residency program who are both matched to somebody else who would prefer to be matched to each other. So in other words, you don't want it to be that a doctor and a residency want to run away with each other. So his hypothesis was that successful marketplaces would be using algorithms that resulted in stable matchings. And what I have on the right-hand side is this observational data that they collected that showed that there was a very strong correlation between whether a match, a labor market match, was using an algorithm that resulted in stable matchings and whether the market succeeded and persisted. And then they took this into the experimental lab and they found they were able to test this hypothesis. They set up a series of experiments that actually showed that this was a very strong relationship. And so this, the Roth-Parenson algorithm, which builds on an algorithm some of you may know, which is called the Gale-Shapley algorithm from operations research, was implemented for the residency match. It's been implemented in, here's the list, tons and tons of places. This is now the gold standard. And the way this was developed was thinking about how do we use the tools of economic theory to hypothesize what's going wrong with a market environment or a collective environment. How do we test it, and then how do we implement it? So in that in mind, I want to move on to talking a little bit about governance. And the goal here is to use these similar tools to say, how can we think about optimal outcomes for participants in a collective decision-making environment, and what kind of factors do we need to think about in design? And so the two questions, again, that I'm going to be looking at are, one, how do we measure the social optimality of a hard fork? Right? So how do we think about whether and when forking is good for a community or not? And the second question we're going to be looking at is, suppose that I implement some of the very popular governance procedures that we see in blockchain. To what extent are these going to be able to coordinate a community on an optimal outcome, whether that includes forking or not? And the goal here is that we don't want to eliminate forks. We just only want them to occur when they're optimal for the community. So I want to start, this is a little bit of math, and this is the model set up for any of you who are interested. And just for those of you who have studied some game theory, the thing I want to emphasize here is that this is a very straightforward setup. This is not an excessively complicated model. And this is actually a really good thing for the results, because when we think about what we find, we don't have to worry about hidden assumptions, playing with what we're able to find. So we're studying a community, a unit mass of individual users in a blockchain community, and we're going to think about them as having a preference over a particular policy. So a great example here is block size. So you can think about, having preferences over two different sizes of blocks, and they're going to be choosing eventually between the status quo and an upgrade. So each user on the blockchain is going to have what's called a value function. So this is the value to that user of participating on a chain with a particular policy. So the policy is a variable, we're calling it J. And the value of participating in a chain is also going to depend on the number of other people on the chain. So in other words, this exhibits network effect. All other things equal, I like more people to be on my chain with me. And we're going to have two different types of users. So we're going to have type A, who are the individuals or the users who prefer the status quo, and we're going to have type B that prefer the upgraded policy. And there's going to be a fraction beta of type A users and a fraction 1 minus beta of type B. And so the first question we want to address again is, under what situations are forks beneficial to a blockchain community? And to study this, we actually don't need governance yet. So we're going to be looking at a situation where individual users are choosing between two chains. So one has the status quo and one has the upgraded policy. And they're individually choosing which one they want to participate in. And we want to know a couple of different things. So first, we want to know, when will having two distinct chains be a Nash equilibrium? And the idea here is that when will it be the case that no individual wants to switch chains and participate on the other one, given what the rest of the community is doing. We also want to know when having two chains is actually social welfare maximizing. So this is the idea that we want to maximize the total well-being of the community. And we're using two different measures of social welfare. Both of these are very popular in economics, and they provide interesting contrasts and insights into what's going on here. So the first definition we're going to be using is called total surplus maximization. So this is when an outcome maximizes the sum of the value for the entire community. The second definition is called Pareto optimality. This is a little bit weaker. And the idea here is that you can't make one group better without making another group worse off. So in the blockchain example, an outcome having two chains is Pareto optimal if putting them all together on one chain would always result in one of the two groups having less value than they do with the two different chains. And so I just want to walk you through the high level of what we find here. So this is a stylized representation of our first set of results. And the line here is this population parameter beta. So this is the fraction of users who prefer the status quo policy. So at 0, there are no users who like the status quo. Everyone prefers the upgrade. At 1, it's the opposite. And so what we find is that the results look something like this. So total surplus maximization is basically considered to be the gold standard of social welfare, right? We've maximized the total utility of the community. So this segment, this area of the parameter space, exists sometimes. It is not always the case that a fork can be total surplus maximizing. If it is possible, the location of this particular segment moves depending on the other parameters in the model. But this is sort of the first interesting insight. A fork can be total surplus maximizing, but that doesn't necessarily need to be true for all situations. At the opposite spectrum, we have these segments here where a hard fork is not in Nash equilibrium, it's not socially optimal. So these are when hard forks fall apart, right? So this is where if we took the community and we put all of one type on one chain and all of one type on the other, they would all voluntarily move back onto the same chain. So if we think about that long, long list of failed hard forks from earlier, a lot of them are probably not Nash equilibria, right? So somebody forked and then it turns out that people wanted to converge again. The third segment is this area where hard forks are Pareto optimal, but not necessarily total surplus maximizing. So this segment always exists. There are always scenarios for which a hard fork is going to satisfy some definition of social optimality. So this is actually good, right? Not all forks are bad. There's always a situation where forking can be good. But it doesn't necessarily coincide with the other definition. And finally, this is the area that I find most interesting. So there's segments of the parameter space where a hard fork can be a Nash equilibrium but not Pareto optimal. And what's going on here is that you have a fork. Individually, no person can, no one wants to change what they're doing, but at least one of the two chains really wishes that they all got up and joined the other chain. So there is at least one of the two chains has ex post regret from the fork. And one of the interesting things about this particular area is if we're looking at the world and we look at some of those areas where hard forks have persisted, absent some kind of collective action mechanism, we don't know actually whether the fork is socially optimal or whether everybody is just stuck in a coordination failure. All right, and just to, before I go on to the governance model, I think I just want to reiterate that that set of results there is one of the reasons why economic theory can be really useful and why we actually sat down to write this paper, right? Because if you think about the start of the talk, there was a question about, when are hard forks good? Are they always good? Are they bad? What kind of scenarios can occur? And by writing out a model like this, we've learned that it may not be the case that a fork can be total surplus maximizing, that there are always scenarios where a fork is socially optimal in some way, and you can actually get forks that are the result of coordination failures where one of the two chains or more is actively unhappy. All right, so now I want to talk a little bit about the role of governance and its relationship to hard forks. So we see a lot of discussion around governance about whether choosing the right voting mechanism can free the world of bad forks, right? If we just pick the right way to tally votes, we would no longer have unnecessary forks. So this is the question we want to explore here. So we're studying a simple setup. There are 4 stages. They're written across the top. So we start with all of the users on one chain that has the status quo policy, and then we're going to have voting occur. And we're going to look at 2 different kinds of voting. We're going to look at them separately. So one type of voting we're going to look at is majority rule, which is just where the policy that more people prefer is implemented. And the other type of voting we're going to look at is called quadratic voting. This is, there's been a lot of discussion around quadratic voting, and the idea here is that the policy that maximizes total surplus is implemented. And the key distinction here is that under quadratic voting, if you have a particularly passionate minority, they can prevail in the voting procedure. So we're going to have voting occur, and then the winning policy will be implemented, and then the losing coalition, if they choose to, can fork. So we're also going to assume what I'm calling naive voting, which is just that people are going to vote for their preferred policy. Right? They're going to assume everyone's staying together on a single chain and just vote for the policy that they like better. So rather than going through all the details of the math, this is one of those things where the results are 3 pages long and filled with inequalities, I just want to walk you through a stylized diagram to give you an idea of the flavor of the results. So this is a parameter space with 2 dimensions. And you don't need to read all of the small type. Just the thing I want you to keep in mind is that as you go from left to right, the policy change that you're thinking about is getting bigger, right? So all the way to the left, you have a policy that's, very, very incremental. If you're looking all the way to the right, it's a big, big policy change. So what do we find? First, the size of the policy change matters. All the way over where the policy change is very small, you don't get forks. Nobody cares enough to fork, right? And so the question here, the voting mechanism, its only role is to coordinate the community on a particular outcome, right? So the question here doesn't have to do with forks, it just has to do think about the question for the voting mechanism is how do we want to think about picking which policy to implement as a group? All the way on the other side for very large policy changes, forks are socially optimal. This is where we want forks to happen. A fork happens and everyone is okay with it. The middle is where we see interesting things. So in this middle section, forks are not socially optimal. At least one of the 2 chains after a fork always has post-fork regret. So what do we see here? Well, first, if we use majority rule, we get forks under the following spaces, right? So majority rule works very well for the 3rd column. Everybody stays together. In the 2nd column, we get forks. And again, these are forks that people wish hadn't happened. Under quadratic voting, we get forks here. So the areas in which you get forks are different, but you still get unwanted forks and suboptimal forks. And so the piece I think is interesting that I want you to take away from this first are a couple of things. First, there is no voting mechanism that is going to eliminate suboptimal forks, right? The voting mechanism will change under what conditions forks occur, but they won't get rid of them altogether. Secondly, you might say, okay, well, this is great. We know when quadratic voting will work. We know when majority rule will work. Let's just design the system so that we're in the right space. If you actually go through and look at the differences between those different squares, they're based on these population parameters that would be impossible to know in advance, right? So you're not going to be able to sit down when your platform is funded and say, we're going to end up in this box, so we're going to use quadratic voting. You're not going to know. In fact, you probably won't even know when you're running the vote exactly where you are. And so I think one of the key takeaways for us, stepping back from this, is that at least when we're thinking about using current types of voting, governance has to consist of more than just a voting procedure, right? So if I'm a community designer and I'm saying, okay, we're still working on the voting, what do we do in the meantime? Well, you want to stay either all the way to the left or all the way to the right, right? You either want to be in a situation where there's going to be a fork and it's what we want to occur, or you want to be in a situation where forks don't happen at all. And so when we're thinking about designing governance, we have to think about the policy proposal process just as much as we have to think about the voting mechanism. And just to conclude, the paper is available online. For all of you who are interested, I encourage you to read it. Happy to share the link. Just a couple of things that I hope you take away from this. The first one is that standard governance processes actually do not copy-paste well to blockchain. And this is a place where I actually disagree with the panel yesterday. I think that economic principles are fundamental for making blockchain systems that work, but you need to design your systems for the specific setting at hand. And I think that this is a great example where taking governance processes that have always been designed and examined under the assumption that people cannot secede, and then applying them to a setting where people can secede results in outcomes that are not necessarily good or would be expected. I think the second takeaway is that governance is about more than just voting. And something I didn't have a chance to talk about, but is also really important, is how you think about communicating the results of your governance. So for example, there's a simple extension of this model where the user community doesn't know in advance what fraction supports each policy. And by going through voting, you actually inform the minority that they have enough people to leave, right? So you have to think about how you're going to communicate both the policy you're going to be using and the results. And I think that there's a lot more work to do, as we all know, to develop effective and practical governance mechanisms. So just, a word of caution that I always think about, there's this famous mechanism called the Vickrey-Clark-Groves mechanism, and it's the perfect mechanism. It produces a socially optimal outcome, it's truthful, it's wonderful. The only problem is that no one's ever been able to implement it. It's impossible. It's just, it has too many assumptions on people. So, we're going to have to think about optimality, but we're also going to have to think about practicality. And for those of you who are interested in learning more, economic design has now been applied to tons of different settings. This is just a limited list. For those, and the common theme for all of these is that introducing economic design allowed the participants in a marketplace or a community to achieve better outcomes than they would have in the absence of that design. So by providing these tools, you actually allow your users to come to better final outcomes. In an area called market design, which auctions and matching are part of, there have been half a dozen Nobel Prizes over the past decade and a little bit more. And for those of you who are interested, I highly recommend Al Roth's book, Who Gets What and Why, which talks about a lot of the ways that he's been able to use economic theory to redesign everything from school systems to kidney exchange. All right, so this is my contact information. Again, my name is Stephanie Hurder. I'm with Prysm Group. Please don't hesitate to reach out on Twitter, Medium, or any of these things. I also want to note that in November, we're going to be teaching a mini course at the University of Southern California School of Engineering. And this is a course specifically on economics for blockchain practitioners. So we're going to be focusing, it's designed for technical people who are working in blockchain, who want to learn more about the relevant areas of economics. So if any of you are interested, please sign up. All right, thanks very much.